do a modal analysis. Make sure that you're doing a modal analysis for everything, so that you'll be more familiar with modal analysis as well as structure analysis. Okay, so taking to the buckling analysis, your static structure is a base for that. So import geometry, browse. Is there any stringer? No, stringer is here. So I'll explain you first what the component is, so that you'll be familiar for what exactly it is. Okay. Okay. So this stringer or this structure, as you are looking, this structure is kind of a thin sheet. Okay, thin sheet which will be typically made. Earlier days, these kind of structures used to made with metallic like aluminum or like any other lightweight materials. Okay, but nowadays this kind of structures are used from composite. Okay, sorry for thing. Okay, so these is the structure, what we say is in fuselage in the sense your aeroplane outer case. As I can show you from the presentation.
Got it, sir.
Got it, right, everyone? What
Yeah.
fuselage in the sense
We are
I'm
aeronautical branch,
talking about?
sir. We are from aeronautical branch only, sir.
Okay, fine. sorry, I forgot that, because in the previous batch only mechanical guys are there. They don't know what exactly a fuselage or engine structures naming. Okay, this is what the fuselage a stringer. Okay, so this typically in the older days this was used with aluminum alloy structures or lightweight metallic structures which have more strength, like typically titanium alloys or aluminum alloys. As nowadays, this is made of composite material, that is, you can say carbon epoxy or CRPF, what we typically call carbon reinforcement fiber, carbon reinforcement fiber. Okay, so but I will not be taking you guys into composites, because it is entirely different. It may request more patience for you guys to check those things. Okay, but I want you people, for this structure, you create a geometry. I'll share this image with you guys. You create a geometry with respect to this drawing. Okay, and analyze your buckling or critical load for buckling. Okay, and the material you can use as aluminum alloy, titanium alloy, and compare the results and suggest your conclusion from the presentation that which material will be having a higher strength by weight ratio. Yes, getting the point what I'm talking about. Okay, so this geometry I have created, so I'll say that I'll share you because you people have already worked on CATIA. That will give you people also one exposure that how do you do your modeling, CAD model, as well as generate that use that CAD model to solve and check which material gives you more appropriate results for calculating a critical buckling load, or which material is best for buckling.
Excuse
Okay,
me, sir.
yeah,
Sir, all in this group, all are doesn't know the CATIA, sir. Don't know the modeling. Only
okay,
few are
fine.
know.
Only
So
few
if
are
you
known.
can you share that model only, sir? Geometry so that we can do the analysis.
Fine, I'll share that. That is not the concern. It is not a hard. I'll share. Okay, fine. I'll share this. What I'll do? I'll share this equations or the values or drawing this drawing as well as the model also. If people are interested to do this model who has done CATIA, okay, then go with this and see the results. And those who people don't know about CATIA or have not trained on CATIA, so they can directly go for using this model and analyze it. Okay, but I'll show how the procedure we do for working on this in general. And again, you need to check for all the three materials, that is, one is default as structure steel. Okay, one as default as structure steel, and other aluminum alloy, or either you can use 6061 or you can use 6065, any one or any two, and also compare that with your titanium alloy. Okay, so that you need to suggest or give a summary of these three materials and come a conclusion that which material would be better to use for the stringer material. Okay, apart from composite, which would be the better. Okay, as an your curriculum exercise. Okay, so why I'm saying this kind of thing or these kind of problems, you'll get an idea in future for your any analysis you do, or your projects of your engineering project or 8th semester projects. You look into any of a geometry or any component of an aero engine, because as you people are from aeronautical background, so you need to choose any of the geometry and you build a geometry and analyze and compare study. You can do it and submit as a project for your 8th semester. That also you can do in future. Yeah, so you can plan for that which component is more critical nowadays, like wing structures or like your fuselage or interior, any kind which will be helpful for your study purpose also. Okay, so just I'm giving a hint. So as I've imported and I'm taking as default structure steel, I'll update mesh. One here you can use either 2D mesh or you can use your hexa elements. But 2D would not give you a proper uh, mesh, because as you have you need to make a node to node or node to node connections to the structure. Okay, so I'll just update method structure update. Now it is automatic multi-zone. No, it is considering as an hexa. It's a 2D or solid. If you only create a plane, then your what we call then your program or your software will take it as 2D. Otherwise, it will consider as solid itself. Okay, fine, no issue regarding that. You generate as a mesh. You take fine mesh or you take coarse mesh will be well and fine. You can see that as it is taking one geometry, you can utilize that as a fine mesh, and you are getting two elements at the string job or rigs, what we call typically. Now for modal analysis, I'll use a fixed support. One end you can fix as a support. Okay. Other for this, this zone is not uploaded. Okay. Now for this, you just solve. You'll get how many more? 6 modes you'll get for fixed support to know your natural frequency of the structure. Then for apply as a boundary condition, previous okay, and then apply a load or pressure. I'll consider a pressure at this end normal to surface. That means I can see take initially 5 MPa. Okay, and just take a deformation. Sorry, yeah, for this deformation also equivalent stresses, and also I'll give a number of buckling mode as 8 or 7 or 6. 6 would be fine. So I'll solve your structure, static structure. Okay, and then solve for buckling. As you can see, like buckling is an only one shot. Only you need to select which static load, static structure your linear analysis need to be assigned for this, and then consider number of mode shapes. Okay, so that is what only update, or you can take as one step increase to do a buckling analysis for the structures. Okay. As you can see, the stresses, sorry, deformation as well as the stress in your component, which is very less due to pressure. So you can say that your buckling load is multiplier is huge as a negative. If I consider same, when I will take this pressure, I will suppress this and I'll add a point load on the same structure. Okay. Okay, 1 second. Okay. So for this force, I'll consider component, and you can say x, negative x would be the critical one. I'll consider as 1000 Newton. And solve for that. And same for buckling. So now we can see there is difference between when you apply a load, that is a load and a pressure. Okay, so that is what the difference. So now the load multiplier is 122.26. I'll just what I'll do, I'll multiply or with 1000, like negative 1000, sorry, into 1000, right? So this will be your critical load. You can say that your critical buckling load would be that value for the structure for static or for structure steel. Now you can see this, your load multiplier is 1. That means for this mode shape, or what I'll show you, for this mode shape, your structure will be deformed, or in that direction, particular direction for the first mode shape. So for the point load, in that direction, your structure will be failing. You can see this with the scale. I can increase. Okay. In the sense, for this load, your center point or your center will have maximum displacement. Okay. So this would be your first mode shape, second mode shape. Yeah. Third mode shape for the same structure. It is like twisted up. Okay.